right, I think we'll go ahead and get started. Welcome to this week's Physics Colloquium, which is also the TAP Gravity Initiative Lectureship. So TAP, if you don't know, is Theoretical Astrophysics Program, which connects physics, astronomy, and planetary sciences. And we have a visitor program, and Aaron Zimmerman is visiting us today and all of next week to interact with anyone who wants. He has a schedule. You can sign up to meet him. And this talk is part of that visit. So if you're not involved with TAP, you should get involved. We have a lot of interesting programs going on, talks, visitors, meet yourself events, various things happening. Aaron Zimmerman was a student at Caltech with Yamei Chen, working on black hole perturbation theory, issues in general relativity. He moved to a postdoc at CETA, where he later was promoted into an associate research position. He was there 5 years, during which time he got involved with LIGO. And he moved to UT Austin as an assistant professor some years ago. And I've written one paper with Aaron. It's a paper I'm really happy about. We're really proud of, and we finished that paper up in August 2017. And if you know about the LIGO events, there was a very interesting event at the time, a neutron star merger that had electromagnetic counterparts. So when Aaron was visiting me here working on that paper during the day, he was also on call, like the person who was supposed to analyze the LIGO data initially if anything exciting happens. And during that week, there were a number of detections that he had to deal with, including the neutron star merger, and so I knew nothing of it. He, to his credit, worked with us all day here on the paper we were writing and stayed up all night working on what became these seminal LIGO discoveries. And so today he's going to tell us more about what's been going on with LIGO.
Thanks, Sam. Thanks, everyone, for being here, first of all. And thanks to TAP and to Sam for inviting me to be here today and in the coming week. Today I'm going to be talking to you. It's sort of a two-part talk. Gravitational waves would be the first part of the talk, where I'm basically going to give an overview of what's been going on in the last 5 or so years, which is about how long it's been since I was last here working with Sam on that paper. And then after that, I will be talking about some more recent work from my own group, using gravitational waves to search for the unexpected. And I'll talk a little bit more about what I mean about that. But to begin with, I need a disclaimer. So many of the results I'm going to be presenting to you in the first part of the talk and later on in the talk as well are the results of the larger LIGO, Virgo, and KAGRA scientific collaborations. I'm a member of the LIGO scientific collaboration. It's a large international collaboration with almost 2,000 members, with groups spread all across the world. And this is not a talk on behalf of the LIGO scientific collaboration, although I'll talk about some of the work from that collaboration. And so let me just say at the outset that when I present to you all the amazing, exciting work that's been done, all credit goes to the global community that have been working on it, and every mistake and stupid thing I say you can blame solely on me. All right, so part one of the talk, gravitational waves. So I'd like to begin these talks by first highlighting the technology, the experiments that have really enabled all of the discoveries I'm going to be talking about. And these are the network of advanced gravitational wave detectors. They're the twin LIGO instruments in the United States, one in Hanford, Washington, one in Livingston, Louisiana. There's a sister detector in there's a sister detector in Europe, Virgo, which is near Pisa, Italy. And the newest member of the gravitational wave network is the KAGRA gravitational wave observatory underground in Japan in the Kamioka mines. Now at their heart, each of these instruments is really a Michelson interferometer, designed to measure very sensitively any relative change in the lengths of two perpendicular arms by using laser interferometry. Except these experiments have souped up every aspect of that Michelson interferometer, along with controlling very carefully every single aspect and screening out every possible source of environmental noise, to the extent to which they can measure a differential change in the lengths of these two perpendicular arms down to the level of 10 to the minus 19 meters. That's less than 1,000th the size of an atomic nucleus. It's a number that sounds impossible, but it's done routinely. And what's more, that is actually the sensitivity we need to get down to detect the imprint of gravitational waves, these ripples in the fabric of space and time, as they pass through the Earth and as they imprint themselves on the detector by shaking these mirrors just this tiny, minute amount. even with these incredibly sensitive detectors, we can only detect gravitational waves so far when they come from the very strongest sources of gravitational waves we know of in the universe. And this is going to be the final orbits and merger of very compact binary systems. So binary systems composed of black holes and neutron stars, which can orbit each other at a significant fraction of the speed of light. This plot depicts the strain, the dimensionless delta L over L that would be imparted on the detector as a function of time for a binary black hole merger. These mergers are divided into three phases. There's a very long in-spiral phase. In principle, this could be going on for millions of years, but we only see the last 10,000 to few cycles of this merger, depending on the mass of the system. During the in-spiral phase, the black holes orbit each other, emitting gravitational waves, sink closer together, orbit faster, and it's a runaway process where the oscillations of the gravitational waves are increasing in both amplitude and frequency. We call that a chirp. The neat thing about the in-spiral phase is we can actually model it using perturbative methods. So by doing expansions in the speed of the binary over the speed of light, we can calculate this to high precision, at least until the speeds get too high. Once the speeds are too large, you need full numerical simulations of Einstein's equations in order to understand how these objects merge together, in the case of two black holes, becoming a final black hole in a violent and sort of nonlinear process. And then afterwards, there's a process called ringdown, which I might have time to talk about near the end of the talk, in which this final merged black hole relaxes to a single equilibrium state, and in the process, this can be understood, again, using analytic methods. One thing I want to highlight on this plot is that gravity itself has no preferred scale. So the time scale here is t divided by the total mass of the system when scaled to be units of time, essentially the light crossing time of the mass of the system. Okay? And what this tells us is that for more massive binaries, these final orbits take longer, the merger frequencies are lower, and because our detectors are only sensitive to certain frequencies, there are systems where we only see the merger and we don't see the lower frequency components. On the other hand, the lightest systems, we don't see the merger. It happens at too high a frequency, and we would only detect this binary in-spiral. And that's a point I'll return to later. Now, even with these amazing detectors, and even with the strongest sources of gravitational waves in the universe, it is still a serious data analysis challenge to make a detection of a gravitational wave event. What I'm plotting here at the top is the raw data from the Hanford detector, as it is. And this is not a gravitational wave signal. This is just noise in the detector. The noise in the detectors is what's called colored Gaussian noise. It's essentially random noise, but with different power and different frequencies. And you can see there's a lot of power in the low frequencies, orders of a few hertz, okay? And there's also a very high frequency fuzz. And buried in here is a gravitational wave, actually a very strong gravitational wave event. And so what is one to do? Well, the first thing you do is you use what you know about the noise in order to try to clean this up and put all of the different frequencies on the same footing. That's called whitening the noise. It's a filter you can apply. And this is what the noise looks like after whitening. It looks a lot cleaner. At least there's no huge fluctuations. But you still can't really tell that there's a gravitational wave event in there unless you know what you're looking for. If you know what you're looking for, you could do a bandpass filter, filter out everything but the wave itself, and there it is. That's actually the very first detection of gravitational waves. We call these things by the time we detect them. So this one's called 150914. It was detected 2015, September 14th. Okay? And this is a very loud signal, which is basically impossible to detect through these sorts of methods. So how do we find these waves? Well, fortunately, there's an answer to the question of what is the optimal way of finding a filter to filter out noise and find a signal buried inside it. And that's known as match filtering using an optimal filter. The idea is you take the thing you're looking for, a theoretical prediction of the signal, and you correlate it with the whitened data stream. This cartoon is going to illustrate that process. When we correlate it, we get this number z. When we take its absolute value, we call that thing the signal-to-noise ratio. That's essentially the strength of the signal. And as I scan my filter over the data, if it matches up and correlates well with the signal, boom, you get a sudden jump in the signal-to-noise. So buried in this whitened noise is actually a nice, strong detection, which you can dig out with the matched filter. In the frequency domain, the match filter is particularly easy to understand. You take the data, you take your prediction, you weight it using the power spectral density. This basically tells you where the noise is large, you downweight the integral. Where the noise is less, you don't downweight the integral, and that produces for you the signal to noise. Now, some immediate questions should pop into your mind. Okay, you need to actually look for what you're looking for with the signal itself, but you don't know what's in the data a priori, so what do? Well, the answer is we then have to do several things to explore parameter space. So one thing we do is that we take a full range of possible systems we could look for, systems that have different masses of the two binary members, and we populate what's called a template bank. Every point here represents a potential gravitational wave signal that are simultaneously filtered across the data at all times. On top of that, we scan these filters over time, and we maximize over time. We also maximize over a phase, and we maximize this signal to noise over the full template bank, and whatever rings up loud enough has the possibility of being a detection. And what's nice is that would be the full story if this noise was well behaved. And the truth of the matter is, this is not the full story. The problem is much harder than this. And the reason is that there are these other things in the data, not just Gaussian noise, but these things that are instrumental artifacts called glitches, which can be quite loud, and worse still, they can actually be shaped just like gravitational waves. So in this time frequency plot, we have a glitch which is going up in frequency as time evolves, just like a gravitational wave signal does. And so the real magic of gravitational wave search algorithms is how they deal with these glitches, and generally all of them apply different signal consistency tests, and which tests they apply is what makes each different search algorithm different from each other. Okay, so that's just the rough idea of match filtering and how we can detect these signals. Once we detect a signal, we'd like to understand what made it, and this is a bit of a more intensive process. When we measure the parameters of the system that made a given gravitational wave signal, we perform Bayesian parameter estimation, Bayesian inference on it. The idea here is our measurement of the binary parameters actually comes in the form of a probability distribution. We actually want to give you information about what is the probability that the masses of the system were something given the data you observed. Okay, that's the posterior probability. So this theta vector is all the different parameters of the system. It's the masses of the black holes, their spins, where they are in the sky, how far away they were, when the system merged. Okay? Unfortunately, we cannot calculate the posteriors from the data. It's impossible. But Bayes' theorem provides you with an equality between the thing you want and some things you actually can calculate. And these three things are the likelihood. This is the idea that you assume that there is a certain signal in the data, and you ask how likely is it that the noise in the data then gave me exactly the thing I saw. Okay? So if you understand your noise, you can actually calculate the likelihood, and that's the powerful idea here. But on top of that, you're loaded down with a few other things. We have something known as priors. These are basically your prior assumptions about what the parameters could be. And this is something where people get into arguments all the time, and this is the thing that people use to sort of badmouth a Bayesian approach to statistics, is, oh, well, you could phrase a prior that could make your measurements anything you want to. So yes, that's true, but the nice thing is you have to actually specify your priors, and generally you try to pick priors that are pretty neutral. But the priors are also good because they can also specify physical constraints, like that the masses have to be positive numbers. No matter what, you have to specify them, and you have to say what you do. The final element is just a normalization factor that makes sure that this probability is all summed to 1. And so what I'm going to be showing you when I show you the results of gravitational wave measurements is going to be showing you plots like these. This is a probability distribution in mass space for the probability that the system of the given masses made a given signal. And that's how we phrase all of our measurements in this field. I didn't mention at the start, but questions are always welcome. I guess the people in the back may have to shout at me because this is quite a big room. But feel free to interrupt, raise your hand if you do have a question somewhere along the way, and I'll try to pause halfway through the talk anyway, since it is a two-part talk, to see if there are any questions. But does anything come to anyone's mind at the moment?
Yes.
Yeah.
So going back to the image of the gravitational wave,
Yeah.
By the looks of the image, I'll just say it looks more like a chirp than a wave. And so I was kind of curious, like, my understanding of gravitational waves is they're caused by two bodies going around each other. So if you get frequent, you wouldn't basically get for lack of a better word, not a sinusoid, but
Yeah,
they're-
absolutely. Yeah. So this is a great question. You're absolutely right. So when the binary system's very far apart, they orbit more or less at a constant frequency, and the in-spiral is very slow. And so this waveform looks much more like a sinusoid, whose frequency is only very slowly varying. Okay? But in the little snippet of the signal I'm showing here, we're close to the end, when the evolution of the binary has gotten to be quite fast. And at that point, it is not well modeled as just a sinusoid. It is, in fact, modeled as a chirp, just like you said. And so, indeed, the end of the signal is this chirp, which terminates in this sort of transition into ringdown. Yeah?
Sorry. Can you go to the next slide on the patient?
Yeah.
Yes. What is each parameter?
Ah, good. I didn't specify this, so this would be the posterior probability, our measurement, given the data, D, and M is a model. You always have to specify a model. We cannot do this analysis without a good theoretical model for the gravitational waves, and that's actually very critical to the whole story. The entire scaffold of all of the astrophysical and fundamental physics things that we can do with gravitational waves hinges on theorists going into their rooms, closing the door, and doing really good calculations to provide us with accurate predictions. I need to be able to know exactly what the gravitational wave looks like for a given set of masses and spins. And that is a whole field into itself. Okay, let me proceed, and we can come back for more questions if there are any later on. I don't mind if I don't get through all my slides. I've got more content that really fits into an hour anyway. So, with the preliminaries dispensed with, let's talk about the observations. Okay, the way that the gravitational wave network functions is we go through a sequence of observing campaigns. We run the detectors for a little while, then we shut them down, and we improve them. And with each improvement, we advance the detectors towards their ultimate design sensitivity. And so in the first observational campaign, that opened up with basically the first detection of a binary black hole merger, that GW 150914 I showed you earlier. 3 detections were made in that first campaign, then it shut down. And then it started up again for the second observational campaign, at which point another 8 detections were made. Then there was a shutdown. And then in the third observational campaign, whose results I'll be presenting to you today, an additional 79 detections were made, leading to a grand total of 90 at the end of the third observational run. Now, each of these observational runs, you can see, is similar in duration. The reason why we're getting more events is because the detectors are getting more sensitive. One of the great things about gravitational wave science is that these observatories are not measuring intensity of light like a telescope. They are measuring the field directly. Now, fields fall off as 1 over distance, not 1 over distance squared. And what that means is if we double the sensitivity of our detector from one campaign to another, we increase our reach by a factor of 2. We increase our volume that we can probe by a factor of 8. We get about 10 times as many detections for a factor of 2 improvement. And so very quickly, we go from 3 to 10 to 100 to 1,000 detections. Okay? That's one of the really amazing things, and it's a transformation we're seeing basically over the span of a few years. Now, after the third observing run, there was a long break. This was to upgrade the detectors somewhat significantly, but mostly this break was impacted by the pandemic. We finally began the fourth observational run early in the middle of last year, and we're currently actually finishing our break in the halfway point of the fourth observing campaign, and in just another week, we will begin the last half of that fourth observing campaign. I mentioned to you that after 3 observing campaigns, we detected 90 events, and this is a schematic depicting these events. Each of these events featured 2 compact objects, black holes or neutron stars, merging together into a final object. And so depicted here are 90 plus 45, 90 times 3 objects. The idea is that each and every one of these systems is composed of a black hole or neutron star, which are produced by the death of a massive star. So in many ways, what we're seeing here is a stellar graveyard. And the idea is we want to study the properties of these stellar remnants, these sort of corpses, in order to better understand the lives and deaths of stars, but also to use them to probe fundamental physics and the history of our universe. It would take me many talks to sort of discuss all the really interesting and exciting physics we can do with these events, and all of the really interesting single exceptional events that lie hidden in this mass. And so I'm just going to quickly highlight for you a few of the interesting cases that occurred during the third observing run. The first new event in the third observing run, again, these things are labeled by these annoying strings, which just tell you the date we detected them, 2019, April 25th. This particular event was the second detection of a binary neutron star. Sam mentioned that first detection, which had electromagnetic observations. The most important thing about that one was, of course, I wrote a paper with Sam that week. But this event was slightly less spectacular, but it's still very interesting for the following reason. This event was the first event to be detected in basically just one detector. Okay, the first confident event that we announced that was detected in one detector. Now that's remarkable because one of the strongest sort of demands we can make to get rid of glitches is to demand that two different detectors both see a gravitational wave with some consistent time delay due to the speed of light. Okay? And in fact, a lot of people are under the impression that we can't make a detection in just one detector. But in fact, this is a plot of one of the detectors one of the search pipelines signal strength, the SNR that I mentioned before, versus a signal consistency statistic. Here's some sort of chi-squared statistic. This distribution here is the background distribution. So this is just pure noise in the detector, how it fills up signal versus consistency space. And this is this particular detection. And so it stands out very strongly from the background, which is what allows you to make this kind of single detector detection statement even in the absence of a second detector running. Now, to be fair, this was detected in the Livingston detector, and Virgo, the European detector, was running, but it was running at a lower sensitivity. And so the result is that we didn't get a very good localization in the sky. You only get a good localization in the sky when you have 3 or more detectors running. And so unfortunately, all we could say to the astronomical community is that this detection was somewhere over that entire half of the sky, which made it hard to search for, and so unfortunately no one was able to find this event in electromagnetic waves. However, we can still learn a lot about this event from the gravitational wave signal. We can measure its properties. And one of the things that made this event stand out is the total mass of this system. The total mass of this system was north of 3 times the mass of our sun. And what makes that interesting is that we have other examples of systems of binary neutron stars that we've seen in our own galaxy. They're pulsar systems. We see them in electromagnetic waves. And this system is a clear outlier from the population of those electromagnetically detected systems. So this is the first indication of a new population of binary neutron stars that for some reason we're not seeing in our own galaxy, probably a selection effect, but this points to maybe new avenues to detect new systems in our own galaxy. Now the next pair of exciting weird signals I like to group together because they were just kind of surprising and spawned a lot of speculation about where they could have come from. One event, 1905-21, was remarkable in that it was the heaviest system detected confidently to date at that time, and it was quite heavy. Most of the systems on the plot I showed you earlier are formed of sort of 30 solar mass black holes merging together, but for this one the primary had about 85 solar masses and the secondary had about 65 solar masses. And this was surprising because the folklore up till this time was that you simply could not have black holes in that mass range. The reason for this has to do with how massive stars live and die. For a star to be massive enough to produce a black hole of such high mass, it was thought that they would go through this thing called a pair instability, where the interior of the star gets so hot that it can actually pair produce electrons and positrons. As soon as you start pair producing electrons and positrons, you lose all your radiation pressure, and the star collapses and explodes in a violent event which would prevent the black hole formation. So there's a lot of things that are possible. One thing this detection sparked was for people to go and revisit their models of stellar evolution. Another one is the possibility that both of the 2 members of this binary are actually second-generation black holes. Each one was a previous merger of 2 black holes that you then have to bring them back together by having them in some dense stellar environment deep in a gravitational well so they can find each other again and have a third merger. Another really interesting event, 1908-14, was our highest mass ratio event by far. So the primary is definitely a black hole, had about 23, 24 solar masses. We measured these masses extremely well, very accurately. But it's the secondary, the smaller member, that's really the surprise, because we can confidently say that its mass was between 2.5 and 2.8 times the mass of the sun. And the reason why this is a weird number is that this is very close to what we think neutron star masses would be, but actually it's a little too heavy to be a neutron star. Most all models of neutron stars have them collapsing to form black holes by that time you make them this massive. And so it's a mystery as to what this object is. Was it the lightest black hole we've ever detected, or is it the heaviest neutron star we've ever detected? We can't tell just from the gravitational waves of this event, but in the future we may see more systems like it, which might help us better map out this space and understand what this system was. The last thing I'll mention was sort of the last big first for gravitational waves in terms of compact binaries. And this was the detection of neutron stars paired with black holes. Up until this point, we had not had a confident detection of a neutron star orbiting with a black hole, but we got 2 of them just 10 days apart early in 2020, and so we published these jointly together in a paper. The first of the 2 detections is less secure. It was again only seen in 1 detector strongly. So again, this is a plot of the sky map, the probability distribution across the sky. It's quite large, thousands and thousands of square degrees. The second one was better measured and better localized, but unfortunately neither of these events were discovered by astronomers in electromagnetic waves. Now one thing we can do is we can sort of go event by event and talk about which ones sort of test our understanding of stellar evolution, test our understanding of neutron star matter, right? But of course, now we're entering in the era of big statistics, right? We have 90 events, and so we can now say things about the population of black holes and neutron stars overall. And so one of the things we try to do is we try to measure the population distribution of binary black holes in the universe in order to better understand stuff about stars. Now, it's still early days, and there's still a lot of modeling dependence of these kinds of analyses. But one thing that holds in all of our analyses is that there appears to be an over density of black holes at a certain mass. These plots take into account our selection functions. The population overall is pretty well fit to a power law, but you have to add an extra peak at around 30 solar masses. Just there's more black holes at that range than in other places. And it's actually not clear why this is. Okay, this is a mystery to be explained still. Another thing is there is a clear dearth of very high mass black holes. These black holes make very strong signals. We would see them if they were there. And except for that one very massive one, 1905-21, we did not detect a lot of high mass black holes. And so this actually gives some indirect evidence for that idea of pair instabilities, preventing the formation of really heavy black holes. Okay, this is completely consistent with that idea. Another thing we were able to do for the first time in 2003, in the third observing run, is actually begin to measure how the rate of binary black hole mergers changes over cosmic history. And in fact, it appears to be increasing as we move back in time. And in fact, it's increasing at a rate completely consistent with the rate of star formation, right? The peak rate of star formation in our universe actually happened at a redshift of about 2. Deep back in cosmic history, stars are forming less rapidly today than in the past. And the way in which the star formation rate translates into a binary black hole rate will actually one day teach us an awful lot about the evolution of binary star systems. And so this is something to keep an eye on as another way we can understand our universe. One thing that's actually really awesome to me is that not just can we measure the masses of these black holes with gravitational waves, we can measure their spins as well. We can actually measure if they're rotating or not. Okay? And so one thing we can do is, although each individual system, we often have fairly poor measurements of their rotation, we can combine all of our 90 events together, and we can try to measure the distribution of spins of black holes. And this is a result. This chi is a dimensionless spin. 0 would be non-spinning. 1 is the theoretical maximum for a black hole. And what we see is that actually there is evidence that that the spins tend to peak away from 0, but there's still a possibility that these systems are not spinning very much at all. Okay, so we're not detecting super strongly spinning systems. Okay, but there is evidence that the spin distribution peaks away from 0, and we do have specific single systems that were definitely spinning. More interesting than the spin magnitudes, though, is this plot, which is the tilt of the spins. We can actually tell how the spins are tilted with respect to the orbital plane. And that actually is an important thing for telling us where these black holes are being formed. There's basically 2 hypotheses roughly speaking. Either the two black holes can be formed together from two stars that were born together, they live out their lives together, they die together, they merge together as black holes. And in that case, we would expect the spins to be roughly oriented with the orbital angular momentum. And in that case, we would expect the distribution of spins to peak at tilt angles close to 90 degrees, okay? Spins standing straight up. On the other hand, another leading hypothesis is that these black holes actually formed apart from each other. They didn't know about each other. And they're brought together by many-body interactions in dense stellar systems. In that case, the spin should be totally randomly oriented. And this spin distribution should be flat. And what we see is that, in fact, it doesn't just peak all roughly aligned. There is evidence for anti-aligned systems. Hence, evidence that there are some of these coming from a dynamical origin. However, it is not just flat. And so that's evidence that some of them actually know about each other and are formed together. And so overall, what we're discovering is that these black holes are probably coming from different places, forming black hole binaries with different properties. And disentangling these different branching ratios, if you will, is another exciting thing we want to do as we detect more systems. So a lot of that was kind of what you might think of as astrophysics, right? We were understanding how stars work, the physics of stars, their evolution. These are really hard physics problems, and there's still a lot we don't know. But we don't just do astrophysics with our binaries, with our gravitational wave detections. We do a whole lot of other fundamental physics, which I won't talk much about because I'm going to spend the second half of the talk talking about some of what my group is trying to do in terms of fundamental physics. But for example, we've used gravitational waves to try to measure the properties of neutron stars, in particular to measure the equation of state of superdense matter, matter that cannot be replicated here on Earth. We also, of course, test our theory of relativity. We do a whole variety of tests of our theory of relativity in order to try to figure out if our theory of general relativity is the correct theory. The merger of binary black holes is a really exciting place for us to test our theory because we really have space-time at its most dynamical. Finally, we also use these mergers as probes of cosmology. Okay, the way we can do this is that each individual system actually gives us an absolute luminosity. When we measure the masses of a gravitational wave signal, we know its absolute luminosity. When we then measure the luminosity we observe, we measure the distance directly. This is very rare in astronomy. There's hardly anything ever that acts as a standard candle. In this case, we call them standard sirens. And so every single gravitational wave event is a distance measure. And if we compare that with some measure of cosmological redshift, the recessional velocity, we can use them as probes of cosmology. That can be done if we compare them with electromagnetic counterparts and locate them in galaxies, or it can be done statistically. But regardless, we combined all of our detections from 03 in order to measure the cosmic expansion rate of today, the Hubble constant, with a value which is totally consistent with what CMB type experiments give us. And this is really interesting to the larger cosmological community because today there's a tension in two different ways of measuring this cosmic expansion, the so-called Hubble tension. If you measure it using the cosmic microwave background, you get a lower number. If you measure it using standard candles and this thing called a distance ladder, basically you build out from nearby going outward, you get a totally different measurement, and they're in quite strong tension. And the hope is that over the coming years, as we tighten our error bars in the gravitational wave measurement, this is going to be a measurement of the Hubble constant with its own unique systematics, which will sort of be completely independent of the other two methods and maybe help resolve this tension. All right, I'm going to move on to the second half of my talk now, but now's a great time to pause and see if there are any questions that people came to mind from the first half. Sam?
Yeah, just the plot where you showed the single detector detection standing up from the noise. You don't have to go back, I don't think. It's just quick. Are the glitches folded into the noise?
Look at this. So this is a great question. Glitches can be extremely strong signals, meaning that you take a match filter, you filter it, and even though the coherence is poor, the SNR, the match filter output, is enormous. So glitches are the things that are populating this wing of the background distribution. They're extremely high in the SNR, but they have very poor signal consistency. So the signal consistency test here is precisely needed to get rid of those glitches.
So you've never seen a glitch that looks really a lot like a gravitational wave in a template? That's what
No, we do see glitches that look a lot like gravitational waves, and there are some like very short signals, like a binary black hole merger that's very massive, that looks so much like a glitch that you should never in that case find that it's going to stand out well in this way, because we're going to rank those against similar backgrounds. Okay, so you're going to compare a given duration of signal, let's say, to a background of glitches which is similar in duration. Okay, so you absolutely do get glitches that look like it, and it will be difficult to make strong statements about, say, a very massive system if you only see it in one detector. But for the lower mass systems, these actually don't look anything like glitches, and they can really stand out. So it's easier to do those. But we can make single detector statements all across the mass regime. It just depends on how strong the signal is and how good it looks. Yeah, but yeah, in the green shirt.
This is like somewhat related to the answer you just gave, but what alterations, if any, need to be made to this Bayesian parameter estimation approach for analysis of like potential LISA data for more massive merger?
Let me come back to that later. So the framework is fine. You just need a model of sufficient accuracy and which can produce systems in the right class. So at the very end, I'll mention LISA briefly. LISA is an upcoming satellite-based experiment. It's going to detect entirely different kinds of systems, but we can use similar methods to model those systems, and we can use exactly the same Bayesian strategy. And in fact, the Bayesian strategy in LISA may well be how we also do our detections in LISA in the end. That's what people are playing with now. Yes, in the very back.
How can you tell the difference between like a black hole merger or a neutron star, or a mix?
That's a wonderful question. I'll answer it partly coming up. But for this particular case, we simply say the masses are consistent with neutron stars. We know there are neutron stars out there. So even though I said this was massive in total, the individual masses of each of these two neutron stars is not an outlier from other neutron stars we've seen. But we haven't seen black holes with such light masses in our own galaxy. And so basically, for many of the systems, we classify them according to mass. If the mass is low enough to be a neutron star, we'd call it a neutron star. If it's high enough that it should be a black hole, we call it a black hole. That's why if it's in between, we scratch our heads. But there's also something I'll bring up in a little bit. One of the powerful things about neutron stars and gravitational wave detections of them is that we can actually measure if neutron stars have a size larger than a black hole directly. We just need a signal that's strong enough, and we've done that in the past. Yes?
You mentioned this excess of 30 solar mass black hole.
Yes.
How significant is that excess?
No, the straight power law models all perform extremely poorly compared to any model which allows for some flexibility here. People have also used more flexible models, models that essentially allow the rate to be different in different bins, and they all prefer an excess here. So it's significant. I don't know how many sigmas that would be, but the data seem to like having this excess pretty clearly. All right. If there are no more questions, and again, I'm here all week, I'm going to move on to searching for the unexpected. And I'll probably just talk about the first topic of two, which is directly searching for the unexpected. So a question I didn't get in the questions just now that usually does come to people's minds is, wait a minute, you just told me you have to model the things to find them. So does that mean we can't find things we didn't already know about? Right? How do we find the unexpected? Right? It's a new way of looking at the universe. We'd better be able to find new things. And the answer is that match filtering does require a model, and so it needs some modifications or some thought before it can be used to search for the unexpected. So first thing I'll say is that we do have unmodeled searches. What these searches do is they basically try to see if there's some extra power in the data in two detectors simultaneously, consistent with each other. And that doesn't require a model, and that can be used to detect things we didn't expect. Cosmic bursts of gravitational waves from cosmic strings, for example. Okay, things we don't have a model for. Unfortunately, those searches are best for short duration signals. So what they've been detecting mostly is the most massive black holes. And they may even be good at detecting those massive black holes because we can't always put all the physics we know about into our models for computational expense reasons. And so these burst searches can incorporate unmodeled physics. Okay? But that means that in this high mass regime, these coherent burst models, these unmodeled things, can find things if they're strong enough. But what about quieter signals that are longer in duration. In that case, we could actually be missing things. Let me give you an example. This plot from two of my collaborators illustrates the idea that if you had, in blue, a binary black hole signal, and in gold, a signal of a system composed of hypothetical objects that are a bit bigger than neutron stars, but still compact enough that they can orbit fast and produce strong gravitational waves. That signal looks a lot like a binary black hole signal, but over time, that extra bit of size actually imprints itself on the gravitational waves and causes a slow dephasing of the template to the true signal to the point to which you could not detect these if they were quiet, long signals. And so this is a potential discovery space. As a bonus, if we focus on thinking about low-mass systems that are composed of hypothetical objects, things that are bigger than neutron stars but smaller than white dwarfs, then we can actually focus on the in-spiral phase alone, and we actually don't need to worry about what happens when these hypothetical objects collide with each other. We need numerical simulations that we don't even have a model for. Okay? Instead, if we focus on the low-mass regime and the in-spiral phase, we can actually model these with just a little bit of a twist of the way we model binary black holes and binary neutron stars. And the idea is as follows. During the in-spiral phase, when the objects are well separated, we can basically model them first as point masses, orbiting each other under the influence of their gravity. And then all of the details about how they differ from being black holes or neutron stars comes in sort of a dressing of those point particles with extra properties. Okay? This is sort of like an effective field theory perspective on the situation, if you think about it in that language, right? These are extra terms in the Lagrangian interaction terms that depend on the properties of the objects. The first one would be the spins. Okay? If these objects are spinning, those spins imprint themselves on the gravitational waves. They change the rate of the in-spiral, they change the binding energy of the system through gravitational magnetic effects, and they can also enhance the radiation. This we already incorporate in our binary black hole models. Okay? They could have intrinsic multipole moments. They could just naturally be weirdly shaped. Okay? But that's not very likely for massive objects. They don't have the internal strength to hold up any kind of shape. And then, really importantly, they can also have polarizability. And what I mean by that is that, for example, if I make an object spin, it naturally flattens out. Okay, that's a polarizability. It picks up a quadrupole moment due to its spin. Okay, so the amount that it picks up is encapsulated in a dimensionless parameter kappa, which for black holes is 1, for neutron stars is of order 10, and so we can actually get away with just setting kappa to 1 in our models, and it doesn't have a big effect. But a hypothetical compact object might have kappa of 1,000, and then we wouldn't be able to detect it at all. Okay? A more famous example is how we measure the properties of neutron stars. Each of these objects feels the tidal forces of its companion, and that stretches it out along the axis between them. The amount that it stretches them out is encapsulated in a polarizability known as the Love number. Okay? And this Love number depends on the internal structure of these bodies. And if we can measure this Love number, its imprint, we can actually measure the properties of the neutron star. And this has been done. Now for neutron stars, we now know this tidal Love number is probably of order hundreds to 1,000. But for a hypothetical compact object, it could be 1,000,000. In which case, again, our current templates would not detect these signals. So now we have a way forward. We can model these hypothetical objects as a normal binary system, but we dress them with these new parameters, and we allow them to range over much larger ranges than we would for binary black holes and neutron stars. And we use those as our templates in a new search. This gives us the ability to directly search for new signals. And that was our idea. Now there's a challenge here. Because we're adding new free parameters to the model, we have a much larger dimensional search space, and the computational cost of the problem just goes crazy. Okay? So one thing we've been working on is we've been working on how to compactify the dimensions here, how to focus on pieces of the problem so that we can still get away with a small dimensional search. That's work that's ongoing. But as a first just test balloon for this idea, we thought, well, what if we focus on systems for exotic stars that don't spin very fast? Let's just assume they have negligible spins. Then the first effect that comes in is this tidal effect. And in fact, it's not just the tides of each of the two bodies, it's some overall mass-weighted combination that we'll call lambda tilde. And for this, the parameters of the system are only three-dimensional, the two masses and the overall tidal deformability of the system. And so this is a three-dimensional search that we can now create actual models for and go ahead and do this search. This illustrates the fact that these kinds of systems would not be detected with standard searches. Okay? The red here is basically at a percent level how well just a binary black hole model can capture these kinds of exotic systems as a function of the log of this tidal parameter. And so for tidal parameters below 1,000, like neutron stars, current searches would do just fine. But as you get above that, you begin to get into a regime where the SNR is severely penalized and you will not see these things very well at all. So what kinds of systems are we talking about? I mean, from my perspective, we're really sticking our necks out. We're just looking for the unknown, right? This is just computer time. We don't have to build new instruments to do this search. We can just do it. So we should do it. We should look to see if there's unexpected things in the data. But over the years, theorists have come up with a whole zoo of potential hypothetical objects from beyond standard model physics that could exist. For example, the most famous are probably boson stars. This is just add an extra scalar field to the universe with some mass. It turns out that it can Bose-Einstein condense into a star with a mass of about the mass of a sun. So boson stars could, in principle, be out there, and they might be detected if they're in binaries. Another really cool idea is these so-called gravitational atoms. This is the idea is that if there's a very light extra field in the universe, something like an axion, and these have become very much in vogue in the dark matter community for a potential model for dark matter. If such a particle exists, period, if it has the right mass, it will just spontaneously form a cloud of Bose-Einstein condensate around spinning black holes. And so these spinning black holes will be a black hole, but surrounded by a cloud of matter with a significant amount of mass. That production of that cloud tends to spin down the black hole's spin to make it lower. And so you might have these slowly spinning, extended black holes out in the universe. And so searches for these gravitational atoms help us constrain these new axion-like fields. And so what did we do? Well, we used a different search code than the standard search pipelines used in the LIGO, Virgo, KAGRA collaborations. That's just because the people I was collaborating with had access to these new search codes. This code was developed out of the Institute for Advanced Study in Princeton, so the community keeps calling it IAS, even though all the people who developed it have moved on, basically. Okay, so this IAS search code is a very sophisticated code. It's capable of detecting all the same things that the LIGO, Virgo, KAGRA codes can detect in terms of binary black holes. And so we were able to modify it in order to run our search. We focused on light systems, but systems that were still not too light, because the lighter the system, the more computationally expensive the search is. And this illustrates our results on the first observing run, second observing run, and the third observing run. These plots just show you the number of candidates versus some measure of their goodness, some measure of how good of a candidate they are in the blue. And the red is for just a background of random noise. And so you can clearly see that all of our candidates are completely consistent with our noise distribution. We didn't find anything. Okay. You might have heard about it if we found something, right? I mean, we didn't find anything. Okay. So what can we do? Well, not finding something is still something. What you can do is you can measure what volume of space you searched, and you can use your non-detection to constrain the rate of these events. And so as a function of mass and tidal parameter, we have some rate constraint, which is actually on the same order of rate as our current actual rate of binary black holes. Okay? Now, I think the big challenge is what to do with this. Okay? It's not so obvious how to take this result from the gravitational wave search and map it onto beyond standard model constraints. Okay? That's going to take a lot of extra modeling to understand if there are gravitational atoms in the universe, if there are these axion particles. Then how much of a rate should we have expected? And therefore, how does this constrain that? And I think that's sort of the work of future effort. But I think what makes me excited about these ideas is it really shows how we can use gravitational wave direct searches to start to explore beyond standard model physics. And so this is basically what I just said. As we look ahead, our main target, though, was to have these stars have spins, because the spin, that extra squashing when the objects have spin, this is the most important leading effect. And we've developed some models which are faithful to the data, which we can try to use. And the project is still ongoing in order to actually do these searches with spinning hypothetical objects, not just tidal hypothetical objects. Okay? So we've got a lot of work ongoing. We had to develop new kinds of template banks. We figured new ways to reduce the dimensionality of our model, and we're still doing this. And I think the big challenge is eventually going to be to connect our rate constraints to constraints on new physics. And the other thing my group works on is the ringdown of black holes. I don't have a lot of time left in the hour, even though there have been some questions. I do want to spend the last few slides giving you a picture of the future. So I'm going to race through these slides rather quickly and just tell you the gist of what we're looking at here. This final emission following the merger of two black holes known as ringdown is particularly interesting because this ringdown happens at a particular set of frequencies. Okay? The ringdown itself has a spectrum which is completely determined by the mass and spin of the final black hole. But it's an entire spectrum of modes. This ringdown can occur in a multitude of different frequencies and decay rates. And the interesting thing is that if we can measure even one of those decaying sinusoidal oscillations, we can measure the black hole's mass and spin directly, okay? Because we get two numbers, the frequency and the decay rate. If we measure two modes, we can do a consistency test. We can do spectroscopy with black holes. We can start to actually probe the structure of the spacetime around the black holes from the ringdown, which is in some sense the excitation of the black hole. Okay, so that's the dream. It was once thought that this dream was very far away, that it would really take future detectors like LISA to realize this dream. But the excitement in the field has been that actually people are starting to argue, and there is still an argument, there's still some discussion, that for multiple systems there's actually evidence that there are multiple ringdown modes observable in the data right now. And running with this, one can provide constraints on deviations from our models from general relativity. So these are constraints by the LIGO Virgo KAGRA collaboration from the O3 data. I'm going to skip what our goal is. Our goal is to try to actually test specific theories by computing how the ringdown spectrum changes if GR were not the correct theory of gravity, but if instead we use a different theory. This idea would allow us to create tailored tests of GR which were much more sensitive than just sort of a null test, and also allow us to interpret the results of a null test if we're ever lucky, and these ringdown tests uncover deviations from GR. I've got a lot of technical slides that would have taught you how black hole perturbations work, would have taught you how ringdown works. This next slide is just to intimidate people so that you know I do calculations. But the idea is it's a long-term program where we've developed methods to compute how the ringdown varies in other theories, and we'd like to do those computations and apply them to actual theories and to actual data analysis. But I'd like to take just the last couple minutes and look ahead. So just to summarize the second half of my talk, I discussed for you new searches for the unexpected. Okay, direct searches for, say, spinning exotic stars, or exotic stars that are not spinning very much and are just tidally deformed quite a lot. And I think an interesting direction here is how to apply these kinds of direct constraints to constrain beyond standard model physics. I didn't tell you about our program of ringdown, but taking a step back again to where the talk started, the third observing run, it yielded a lot of discoveries and a lot of puzzles, some of these weirdo events that we can't really yet explain. We've already finished the first half of the fourth run. We take a break halfway through. And in just that fourth run, we've already netted as many signals as we saw in the third run. Okay, so this is this growth of the number of signals that is going very rapidly. We're going to start the next half in April. And in the coming years, we're going to continue to improve the detectors as they approach and are going to exceed their design sensitivity. And along the way, we'll have additional detectors joining the network, like KAGRA as it becomes more sensitive, and another LIGO detector they want to build in India. This is just a splash page. All of our candidates are publicly available. We send out public alerts to the astronomical community along with sky localizations so that people can try to look for these right away with electromagnetic follow-up. But even more exciting than what our current generation of detectors are going to do is what we might be able to do in the future. people are already starting to plan for what we call third-generation detectors. These are really ambitious designs. One is the Cosmic Explorer concept in the United States. Our current LIGO detectors are 4 kilometers long, and the idea is, how can we make this thing 10 times more sensitive? Make it 40 kilometers long. It's a really simple idea. It's a really crazy idea, but it actually is really beautiful. Because by multiplying our sensitivity by 10, as I'll show you in just a second, we can really do qualitatively new science. In Europe, there's a long-term program to build a 10-kilometer triangular gravitational wave detector deep underground to screen it from seismic noise. This is called the Einstein telescope concept. The reason we should build these detectors is this plot here. These curves are how far away we can see at different masses. For Cosmic Explorer, for binary neutron stars and above, we would detect systems all the way out to redshift 100. That is well before the first stars ever formed. That means we would see every single binary black hole in the entire universe all the time. Every single merger of binary black holes will be detected by these third-generation detectors, turning them into really cosmic discovery instruments. In addition to the ground-based designs, there's the LISA detector concept that was mentioned before. This is a satellite mission. It's a trio of satellites that's in an Earth-trailing orbit. The distance between them is on the order of 2 million kilometers. And this has actually recently been adopted by the European Space Agency. So it's actually reached the final stage of acceptance. It's definitely going to fly. They're going to start building this instrument. This instrument, getting it off the ground, allows it to look for gravitational waves at frequencies that are not observable at the ground, much, much lower frequencies. Our ground-based detectors can detect things in the hundreds of hertz. These go down to the millihertz, where you'll detect entirely new classes of systems, like supermassive black holes, which merge together in their galaxies with signal strengths 1,000 times those of signals we're seeing so far. It's also going to discover a lot of systems in our own Milky Way galaxy. White dwarf stars, these are a different class of stellar remnants, they orbit each other at frequencies which are in this millihertz. And we'll see them throughout the whole galaxy, allowing LISA to also be sort of a way of doing galactic archaeology, understanding the history of stars in our own galaxy by looking at their stellar remnants. So it's a really exciting time coming up where we're going to have new detectors on the ground and on the space. And I'm very excited. And I'm going to finish my talk here and thank you for your time, with hopefully some more time for questions.